Hi everybody, welcome to this video on definite integrals. This is our 7th video in our video series on integration. So to talk about definite integrals, in our last video we learned that the definite integral is the limit of a Riemann sum of a continuous function on a closed interval. And we'll review this now. If we have a look at the plot on the right hand side of the screen, here we have the plot of a continuous function y is equal to f of x, highlighted in blue. That's being plotted on a closed interval from x is equal to a to x is equal to b. What we want to do is we want to construct a Riemann sum from this function. So the first thing that we do is we divide up or partition our interval from a to b into a number of sub-intervals. You can see that we've done this on the plot here. So our first sub-interval, that corresponds to x0 to x1. Our second sub-interval corresponds to x1 to x2, and so on. So the next thing we do is, inside each subinterval, we select a number from the x-axis. So the number from the kth subinterval is referred to as ck. We then make a rectangle from the base of each subinterval and the height of the number f of ck. So to explain this, if we have a look at the plot on the right hand side, for that first subinterval there, from x0 to x1, what we do is we select an x value from within that first subinterval from x0 to x1. And we've called that x value, we've called it c1. Then we work out the corresponding y value for that x value, which is f of c1, and we've plotted the point c1, f of c1, in a red dot there on the plot. So what we do is, at that first subinterval, we make a rectangle from the base of the interval from x0 to x1 and the height of the number f of c1. And then we construct a rectangle for each sub-interval in the same way. So if you have a look at that second sub-interval from x1 to x2, we've selected an x value from within that sub-interval and we've called it c2. We've worked out the corresponding y value for that x value, f of c2, and we've plotted c2 f of c2 with a red point on the plot. Then we've made a rectangle from the base of that second subinterval and the height of the number f of c2. So as we've made a rectangle for each subinterval, we've ended up with all these rectangles on the plot. So the next thing that we do is, for each subinterval, we calculate the product f of ck times delta xk. So our f of ck, that's the height of our rectangle, and the delta xk, that's the length of our subinterval. So for each subinterval, we calculate the product of f of ck multiplied by delta xk. And this product can be positive, negative, or zero, depending on whether f of ck is positive, negative, or zero. And then we take the sum of the products. So our sum, s underscore n, is equal to the sum from k is equal to 1 to k is equal to n of f of ck multiplied by delta xk. And this sum is a Riemann sum for the function y is equal to f of x on the closed interval from A to B. And its value depends on the partition P and the choice of numbers ck. Because we can imagine that if we had divided up our interval from A to B in a slightly different way, say if we used shorter subinterval lengths or longer subinterval lengths, or if we'd chosen, say, different ck values within our subinterval, which would have then given us different f of ck values, well, that would have corresponded to different rectangle heights. So if we'd used, say, smaller subinterval lengths, that would have resulted in shorter rectangle bases. And you'd imagine that the sum of the products of f of ck times delta xk, that would then have a different value. So the value of the Riemann sum, that depends on the partition P and the choice of the numbers ck. So we can make the lengths of the subintervals smaller and smaller using more and more rectangles. And we're going to do this now. If we have a look at the plot on the right hand side of the screen here, and while we're watching the plot, watch how the rectangles approximate the region between the function curve and the x-axis. So we've made the subinterval length smaller, and now we're using a larger number of rectangles. And as we do this, the rectangles approximate the region between the curve and the x-axis with increasing accuracy. Here we'll make the interval length shorter again. So the rectangles again approximate the region between the curve and the x-axis with increasing accuracy. And we can keep doing this as the lengths of the subintervals approach 0. So the Riemann sums have a limiting value as the lengths of the subintervals approach 0. The limit of the Riemann sum of the continuous function on a closed interval is the definite integral of the function. For a non-negative and integrable function, so for a positive and integrable function, this limit is the area between the function curve and the x-axis over the closed interval. The definite integral is the limit of a Riemann sum of a continuous function on a closed interval. All continuous functions are integrable. If a function f is continuous on a closed interval from a to b, then its definite integral over a to b exists. Using mathematics, the definite integral can be described as the limit as the norm of the partition approaches 0. So the length of the longest subinterval, as that approaches 0, we write that as a capital letter P between two pairs of parallel lines. So the limit as the norm of the partition approaches 0 of the sum from k is equal to 1 to k is equal to n of f of ck times delta xk. And that is the definite integral. Next thing we're going to talk about is derivative notation and definite integral notation. Before we learn about how to write definite integrals, it's helpful to revise the notation for the derivative, because we're going to see that there's some links there that helps us to understand the notation for definite integrals. So we'll start talking about very briefly about the derivative. The derivative is the instantaneous rate of change of a function. It's the change in the y value of the function per the change in the x value as the change in the x value approaches 0. So another way to say that is that the limit as delta x approaches 0 of delta y, change in the y value, divided by delta x, the change in the x value, that's equal to dy dx, the derivative of our function. Now, looking at this notation, as our delta x, our change in the x value, as that approaches 0 in the limit, we switch from using the Greek delta letter for difference to instead using the Roman d letter for differential. And you'll see that we use similar notation for the definite integral. To talk about definite integral notation now. In definite integral notation, as delta x approaches 0 in the limit, we again switch to Roman letters using d instead. So the limit as the norm of the partition approaches 0 of the sum from k equals 1 to k equals n of f of ck times delta xk, that's equal to the integral from a to b of f of x dx. That's here in this equation here at the top of the screen. So as delta x has tended to 0, we've now got a differential dx. And the Greek capital letter sigma, which represented the sum, that becomes an elongated Roman s letter, still representing the sum of the products f of x dx. So instead of choosing one f of ck value from many inside each subinterval delta xk and then evaluating the Riemann sum, we're summing all products of the form f of x dx as our x value goes from a to b. And by doing this, while doing this, we stop using the k and the n symbols. So to have a look at this definite integral notation, we read this as the integral from a to b of f of x dx. Or we could read it as the integral from a to b of f of x with respect to x. So looking at each part of this notation, what it is, that a, that's our lower limit of integration. That b, that's our upper limit of integration. And that elongated Roman s, we refer to that as our integral sign. The function f of x, we refer to that as the integrand, and the dx, that's telling us that x is the variable of integration. So to talk now about the area under a curve again. The area under a function curve y equals f of x from x equals a to x equals b, that is the integral of the function f of x from a to b. If f of x is a non-negative function, so a positive function, and is integrable over a closed interval from a to b. So this is very useful for us in performing practical calculations, as we'll see later on. So to talk about evaluating a definite integral, we can calculate a definite integral using the following equation shown here. Different sources will refer to calculating a definite integral as evaluating a definite integral. So to look at this equation here, the integral from a to b of f of x dx, that's equal to capital F of b minus capital F of a, where capital F of x, that's an antiderivative of the function f of x. So capital F of b, that's an antiderivative capital F of x where x is equal to b. And capital F of a, that's an antiderivative capital F of x of the function f of x where x is equal to a. So to evaluate a definite integral, we can find an antiderivative, capital F of x, by finding the indefinite integral of the function f of x. Because the indefinite integral gives us the set of all antiderivatives. So what we can do is we can remove that constant of integration plus c, and that gives us one antiderivative of the function f of x. And if we can find an antiderivative of the function f of x, we can then calculate the definite integral using the equation above there. So we're going to do this now. We're going to use integral evaluation notation. So we're going to write capital F of b minus capital F of a in a particular way. We're going to write it as capital F of x, our antiderivative, with a vertical line and a subscript a and a superscript b. By doing it this way, this lets us show the antiderivative in an intermediate step, and it lets us write it in a compact way. So here we've got a worked example of evaluating a definite integral. We want to evaluate the integral from 0 to 6 of x squared dx. So to start off with, we can use our formulas for indefinite integrals to find an antiderivative. From our formulas, the integral of x raised to the power of n dx, the indefinite integral, that's equal to x raised to the power of n plus 1 divided by n plus 1 plus c. So that result, that's giving us this set of all antiderivatives of our function. So if we remove that plus c, that gives us a one antiderivative of our function, x raised to the power of n plus 1 divided by n plus 1. So if we substitute in n is equal to 2 there, solving for our f of x is equal to x squared, we get that an antiderivative of x squared is x cubed divided by 3. So to get back to our definite integral, the integral from 0 to 6 of x squared dx, that's equal to our antiderivative, x cubed over 3, evaluated from 0 to 6. So our integral from 0 to 6 of x squared dx, that's equal to x cubed over 3, evaluated from 0 to 6. So that's going to be equal to 6 cubed divided by 3 minus 0 cubed divided by 3, which corresponds to our f of b minus f of, that corresponds to our capital F of b minus capital F of a, where our b is equal to 6, our a is equal to 0, and our capital F of x is equal to x cubed over 3. So our 0 cubed over 3, that's going to work out to be just 0. So we're just left with 6 cubed over 3. That is equal to 216 over 3, which works out to be 72. So our integral from 0 to 6 of x squared dx, that's equal to 72. So in this example, we used the integration formula for x raised to the power of n to find an appropriate antiderivative. To find the antiderivative of other functions, we can use the appropriate indefinite integration formula for that function. So to summarize, we've reviewed our understanding of a definite integral as a limit of a Riemann sum of a continuous function on a closed interval. And we've learned how to write a definite integral and what the notation represents. We've also learned how to calculate a definite integral with a worked example. With future videos, we're going to build on this and develop on it further. We're going to talk about the theory behind the equations that we've looked at here, and also we're going to see how they lead to very useful practical calculations. I hope that you found this video useful and helpful. Thank you for your time, and see you next video.